Okay, so in this video we're ready to take a look at some examples of finding volumes by cross sections. And so the region that we're going to start with is going to be the region bounded between the parabola and the x-axis. And we're going to take that region, we're going to rotate it around the x-axis. That's going to give us our three-dimensional solid in which we're going to find the volume of. So just like any kind of area computation, we're going to start with a graph. Now, even though we're talking about volume here, I'm going to focus mostly on the part, just the parts that we need. Okay, so we know that this is our parabola that opens up and down, and this is going to be the region that we're going to take. So you know what, maybe I'll go ahead and actually erase there and there. That's the region that we're going to take, and we're going to rotate it around the x-axis. Now, some people prefer to draw the three-dimensional solid. I don't, because I feel like more stuff gets in the way than not. But what you have to remember is this is just half of your three-dimensional solid. If I were to take this thing around the x-axis, you would then of course have the bottom half down here. The reason why I say that you don't need anything else is because, remember, the radius is going to be half of the overall length. So I think what we have up here should be sufficient. Now, another thing that I like to do here is I like to go ahead and put in this vertical bar, much like I did for area. If we are using cross sections like we are, and we're going around the x-axis like we are, we would want to put a vertical bar in here. Because remember, as this goes around, our radius is going to be defined by this guy being the top and this guy being the bottom. Okay? So, let's go ahead and get this set up. We would have our volume on some interval from here to here, which I'll get to in a minute. We would have our pi and then our radius squared. Well, that blue line is our radius. So that blue line represents the 9 minus x squared dx. Okay? Now, this one, as you can see, as we go around the x-axis, would not have a hole in it, right? So we wouldn't have to use that top squared minus that bottom squared. But as I pointed out to you at the end of the last video, you certainly could. The volume would be pi, the top squared would be this, minus the bottom would be y equals 0 squared dx. So again, those are the same things. If you only prefer to view it like this, where you have the top squared minus the bottom squared, that's perfectly fine. If you want to view it like this, that is also perfectly fine. They're the exact same thing. Okay? Now, when it comes to the bounds here, it looks like we're going to need to figure out where the parabola crosses the x-axis there and there. So if you take this and you set it equal to 0, you would find out that that's going to be a -3 and a 3. So I'll go ahead and drop those in, and we have our setup. Now, these problems do get a little messier in terms of the computations. For example, this one ends up being 1296 pi over 5. And so a lot of times, guys, you'll see it on a project as well. I will just have you do the setups many times. Now, my math lab is going to want this as an answer, but on projects and stuff, these are the setups that I would be looking for, where you have your bounds, you have your formula, you have your functions, and you have your differential there, the dx, off to the side. Okay, so for this one now, same basic idea. We're going to take the region enclosed by these two curves, and we're going to rotate it around the y-axis, creating that three-dimensional solid in which we'll find the volume of. So let's go ahead and start with the picture here. Our picture in this case is going to have our sideways opening parabola there, and we'll have a line that looks something like this cutting through. Okay, so this is our region right here, and we're going to go around the y-axis. So hopefully you're noticing this is the first example we've worked going around a vertical axis. In this case, it means we're going to have a dy type problem. So going around a vertical axis, being a dy type problem, I'm going to put my horizontal line in, which is going to help me identify the right and the left as I move forward with this. So the volume now is going to be the integral pi, and we're going to have right squared minus left squared. Just like earlier we had top squared minus bottom squared, our right is going to be the y plus 6 squared minus the left squared, y squared squared, dy. So this is our right squared minus our left squared. All right, so we've got our right being the line and our left being the parabola. Okay, so really not much different in terms of how to get this set up. I do want to point out to you though, remember, if we choose to go dy, then these have to be all y's. There can't be any x's in there whatsoever. Additionally, these have to be y values as well. Now to find those y values, as you've done probably many times, you would take the two curves, you'd set them equal to one another. So y squared equals y plus 6, y squared minus y minus 6, which factors into y minus 3, y plus 2, and then therefore y equals 3 and y equals negative 2, which I would always encourage you to circle back and make sure those numbers make sense. There's our negative 2, and over here would be our positive 3. So I'll drop those numbers in, negative 2 and 3, and there sits our setup now for this particular problem. Answer comes out to be 500 pi over 3, but for a setup, like I'd be asking for in some of the written work, this would be fine. All right, so for this particular problem, it's ultimately going to be the same thing, but we're going to have to take another bit of information into consideration. Area between these two curves, we're going to revolve it around y equals negative 1, not necessarily the x-axis or y-axis, but now the axis of y equals negative 1, and we're going to compute the volume. So let me go ahead and sketch the picture in here real quick. And we've got our parabola that opens up. We've got our parabola that opens down. And so the region that I'm looking for is going to be this right here. So maybe I'll erase part of what I don't want just so the picture doesn't look so messy. So if I erase this guy here, erase that, this, and this, that's going to now be the part that we take around y equals negative 1, which is going to be down here. Now, in the earlier example when we went around the x-axis, if you remember, using this method, this is where we draw in the vertical line and we identify the top and the bottom, okay? Now, the reason we did that is because we wanted to identify the radius. Remember, half of my picture is missing, and so what you currently see is the radius. But because our axis of rotation is not y equals 0 anymore, but instead y equals 1, we're going to have to take that into consideration for the overall radius. Okay, in fact, when we talk about the radius, it's not just going to be the blue. The top would actually need to be this right here, and the bottom would actually need to be this right here. So let me show you what this looks like now as we get it set up. So our volume would be the integral with our pi. And then we would have our top. And I keep saying top. Well, that's going to be the top of the radius part, if you will. Well, that's going to be, in this particular case, from here all the way down to here. And from here all the way down to here is going to be a height of 8 minus x squared. 8 minus x squared would get us from there to there, plus an additional 1 unit. So we would need to have 8 minus x squared plus an additional 1 unit to cover the gap, if you will, from here to here. Then we're going to have minus the bottom squared. Well, the bottom would be this guy here, and that's going to be our x squared, but plus an additional 1 unit, right? This little guy from here up to here, that's going to be x squared, but we need to go from here down as well, so add an additional unit, squared with our dx. Okay, so that's why earlier I said, don't get all hung up on these formulas. The formulas are great ways to start thinking, but really, if you view this as a geometry problem more than anything, it's going to make a lot more sense. So just remember, the blue, while not incorrect, doesn't give us the full picture because we've had to extend our radius an additional unit on each of those functions. The only thing we're missing now are the bounds from here to here. They're x's. I know that because we have a dx. And so to find that, we would then go ahead and take both of these, set them equal to one another. So an x squared equals 8 minus x squared 2x squared equals 8, x squared equals 4, or x equals plus or minus 2. We'll drop those in, negative 2 to 2, and this would then be our setup for this particular problem. Answer on this one is 640 pi over 3. All right, so let's take a look at another one now that'll hopefully drive home that radius needing to be manipulated a little bit similar to this one. All right, so in this one, we've got these two curves. We're going to find the area of it. We're going to revolve it around x equals 5, and then compute the volume of that solid revolution. So our picture is going to look something like this to start, where we have our parabola looking like this, and our line looking something like that. So our region will be this guy right here. I'm going to erase just a little bit of this to make it not so messy. So that's the part that we want to focus in on. And we want to take that now around x equals 5. So x equals 5 would be right here. Okay, so as we go around x equals 5, there's a few things that I notice. The first thing is that we're going to need to go dy in this particular problem. And so if we go dy, we know that we would draw this horizontal in here. And we would also know that the radius now is going to need to be changed by these extensions, okay, much like the last one. Now, before I get into this too deep, since we're going to be dy, we also have to remember we can only have y's. So I'm going to need to solve each of these functions here for x, okay? So these functions for x, the first one would be an x equals plus or minus root y, and the second one would be x equals y over 4, okay? So when it comes to getting this set up, I've said it a lot, top minus bottom, right minus left. But where did that come from? That came from big minus little, big minus little. And if we want to talk big minus little, our big is actually going to be the left minus the right in this case, because of the axis of rotation being to the right of our actual region. So we're going to have our left, which is going to be this guy right here, but we need to represent it in terms of the axis of rotation being at x equals 5. So how do I represent this right here? Well, that's going to be 5. 5 is from here all the way over minus this gap right here. So 5 would be from here all the way over minus this gap. And that gap is going to be our line. Our line is the y minus 4. So let me drop this pi in here because it's always there. We're going to have 5 minus y over 4 quantity squared. Then for the other one, for this guy, we're going to have 5. 5 is from here all the way over to here minus this right here. And that's going to be the parabola, the plus or minus root y. But because of how it's the positive side of the parabola, ours would be the positive root y. So now we've got a minus 5 minus root y quantity squared dy. Okay, so again, this is a really good problem in emphasizing not formulas, but basic geometry. If we're taking this thing around the axis of x equals 5, then your radius for each of these would have to then be, of course, shortened from 5. They're shortened from 5 by an amount of y minus 4 and root y, respectively. So the only thing we're missing now are the bounds. To come up with these bounds, remember they have to be y's. We're going to take these two things and set them equal to one another. So we would have plus or minus root y equals y over 4. I'll square both sides, giving us a y equals y squared over 16. Multiply the 16 over, move everything over to one side, factor out the y, and we get a y equals 0 and a y equals 16 out of all of this. Now remember, the 0 would be right here, which was to be expected. The 16 would be this guy up here. Okay, so when I drop those in, I get a 0 and a 16 there. This would be our setup for this particular problem. And when you compute it all, you get 64 pi as your final answer.